Just outside the urban center of Ho Chi Minh City in Vietnam's Binh Duong province, the Cum Ho tire plant operates on a scale, turning out thousands of complex composites every day. From a distance, a standard car tire appears to be a solid, uniform slab of molded black rubber. If a tire were actually a single thick block, it would fail within miles. When thick rubber deforms under a car's weight and rebounds against the pavement, it generates internal friction called hysteresis. Because rubber is a poor conductor of heat, a solid block would trap that energy in its core until the material reached its melting point. To shed this heat while supporting the vehicle, engineers use a split design. They combine a rigid inner skeleton that maintains the tire's shape with a much thinner, pliable tread layer that grips the road without building up fatal levels of internal friction. This requirement means tires cannot be poured into a single mold. They must be assembled as a series of specific, functional layers. The process begins with harvesting natural latex, the base material that provides the tire with its fundamental elasticity. Inside the factory, this natural sap is combined with synthetic rubber and over 20 chemical additives designed to alter its durability and heat resistance. At this stage, the material is a formless, sticky compound. The machinery is simply working to ensure the chemical ingredients are distributed evenly throughout the batch. Before the rubber can be shaped, technicians lower the temperature of the mix. This prevents early curing, keeping the rubber soft enough to be pressed into thin components. The compound is then fed into an extrusion line. Massive steel rollers apply enough force to squeeze the raw rubber into perfectly flat, geometric sheets with a specific, uniform thickness. Depending on the recipe used, these sheets will become different parts, such as the airtight inner lining or the thick outer skin. They are cooled and wrapped in cloth to prevent bonding before the assembly line. By converting the bulk compound into these organized 2D materials, the factory prepares the components for the 3D building process. These individual sheets are delivered to the building zone, where the internal architecture is finally established. Assembly involves stacking rubber sheets in a specific sequence. A rigid steel bead wire wraps into the inner edges, providing a structural skeleton. Finally, an extruded outer skin wraps around the inner layers, forming a cylinder held by raw tackiness. This object has the correct shape, but it possesses no structural integrity. At this point, the layers are simply stuck together. The friction of high-speed driving would cause them to separate and peel apart immediately. The assembly process creates the blueprint for the tire, but it requires a chemical transformation. The layered cylinder is moved into the curing department, where the final physical properties are set. It is placed inside a high-pressure mold that uses steam and heat to press the rubber outward against the steel walls of the machine. During this phase, called vulcanization, heat triggers a reaction between the sulfur and rubber molecules. This creates permanent crosslinks, fusing the independent sheets into a single, seamless object. The mold acts as a forge, removing the seams between the layers and setting the final tread pattern into the surface. When the tire comes out of the mold, it is scorchingly hot and finally possesses the rugged exterior required for the road. Because a tire spinning at highway speeds must be perfectly balanced, even a tiny variation in the thickness of the layers can cause the vehicle to vibrate. Precision sensors spin the finished tire to locate its single heaviest point. Technicians mark this spot with a small dot, allowing for perfect alignment when the tire is eventually mounted to a car. Before it leaves the factory, each unit undergoes a final visual inspection and bead lubrication to ensure the structural seals are intact. A finished tire is a bundle of dozens of distinct materials, each designed to handle a different physical stress. By fusing these separate, fragile sheets into a unified structure, the factory creates a tool that can survive 60,000 miles of constant road friction.